Well, hello everyone, and welcome back to Adrian's Digital Basement. This is part 2 in the IBM PC 5150 repair series. If you haven't watched part 1 yet, I recommend you do that first, as this is a continuation where we left off in part 1. In that part though, this motherboard wasn't working at all, and I kind of got it working to the point where it was showing some signs of life, but it still wasn't working. It wasn't actually booting up properly. So in this part, we're going to fix this motherboard and get it fully operational so it can run DOS and games and all those things that PC 5150s do. So without further ado, let's get right to it. Before we get started with the video, I want to make a little announcement. I'm going to be at 3 upcoming Vintage Computer Festivals. The first one is at the end of July in Atlanta. That's VCF Southeast. Then after that, I'm going to be at the VCF West in San Jose. And then after that, I'm going to be at VCF Midwest again, and that is in Chicago. I'll have all the dates on screen here because I don't remember them off the top of my head. But like all the VCFs I go to, if you want to come meet me in person, well, go find me at those shows. That's it for the announcements. Let's get back to the video. Okay, let's continue the logical thinking to try to figure out exactly what's wrong with this 5150 motherboard and get it working. It's been a few days since I last worked on this, and I've been thinking through what might be the problem now. First, we need to double check and see that there's any activity on the CPU when we power on the machine. If there is, then it's quite possible that some of this soldered RAM right here is causing a problem. But actually, there could be problems with this other RAM as well, because a bad RAM chip here can totally stomp on a bit, take out the entire row of RAM here. Also, the ROMs here, I've had ROMs go bad on these as well, which can cause the machine to not boot up. But first things first, let's take a close look at the activity on the CPU when we power this machine on, and that's with the oscilloscope, of course. Let's just see exactly what it's doing. When I was editing the video for part 1, I noticed that after fixing the motherboard while replacing that bad chip, I had the scope probe on the non-maskable interrupt pin and not on AD0 when I was power cycling the computer. So let me put the probe on the correct pin this time, which is AD0. Let's bring the scope up and see what happens. Oh, okay. That right there is some actual activity on the board. Now, there's no reset button on this machine, so I could just push reset normally. I have to power cycle it, but it looks like the CPU it's executing code. So that's a really good sign. So what I'm going to do is I'm going to go through all the address lines, just make sure we see normal activity on all of them. And I'm going to say that looks normal. I don't want to see any levels that are like halfway up or whatever. I want to see like a full range of the signal, and we are. I think I'm on AD4. Looks good. AD5, that looks good as well. AD6, looks good. Finally, AD7. Okay, so the CPU seems to be running for a little bit and then crashing. That kind of goes back to what I was saying before, bad ROM, bad RAM, but it also could be some other peripheral chip on the board that's also bad. Let's take a look at the status output on the CPU. Remember that the CPU is running in maximum mode, not the minimal mode, and that's set up by the motherboard by one of the pins that's grounded. And that means that these pins here, 26, 27, 28, are these status outputs, and this will tell us what the CPU is doing when it froze up. Looking at the first page of the datasheet, remember that all of the pinouts or the descriptions here in parentheses are when the CPU is in maximum mode, while everything over here is on minimum mode. That kind of threw me for a loop at first when I was doing part 1, when I didn't realize the difference there. And we're starting out on S2, pin 26, and we are getting a high as the output. S1 is also high, and finally S0 is high. So we're getting high, high, and high. Passive. What? Let's turn the thing off and on. Let's just see if there's kind of activity on here as it's running. Yeah, okay, it did stuff, so that's a good sign. So passive, what does passive mean? We know from part 1 that the ready pin here, which is on pin 22, is pulsing, even though it's in this frozen state. So there it is pulsing. So that part of the motherboard circuit is working properly. I am really encouraged by the fact that this CPU is obviously executing some code. It does it for a little while and then stops. That means that it's not such a bad problem that the computer is unable to execute any code. And that brings me to what we can do next. We can try using a diagnostic ROM on this computer, something that will hopefully initialize the video card or use the speaker to give us a little bit of a clue as to what's going wrong on this machine. There is actually one thing I want to check before we do that though. Let's double check that the ROMs are actually installed in this board properly, because I haven't actually done that right now. So I have a photograph here I found online of all the ROM chips in this machine, and this is for a 64 to 256K board, which is exactly like this one. And starting at the top here, 150-1476, which appears is exactly what's in the board. Then we have 23, 22, 21, and 19. And it looks like we have 23, 22, 21, and 19. All right, so that means that the ROMs that are in here are actually in the correct orientation. I worried that because that one clock generator chip had been removed from this board, maybe people had messed with the other chips as well. So it's always worthwhile to double check that. It took me a little while to find this picture though, and it's funny, I couldn't immediately find a resource saying, hey, these are the ROM part numbers and they need to be in these sockets. So back to the diagnostic ROM. So there's a really good page on -0degrees.net as well about this diagnostic ROM that exists for the 5150 through the 5170, the IBM PC-AT. It's made by Supersoft/Landmark. I think Landmark ended up buying them. And it goes into quite a bit of detail on how you go about using these ROMs. Once you have a motherboard that's actually trying to execute code, that's when it's time to use this ROM. We could have tried this right from the start, but definitely it wouldn't have done anything because we know that this motherboard wasn't running any code, but now it is. Well, it looks like it is. And this is why it matters. Because the regular post or power on self test that IBM does has a bunch of tests that happen when you first power on the machine, and then you can have a failure at any time, and the machine just simply halts at those failures. It takes a little while before it even initializes the audio or the beeping capability of the computer. Then there's a bunch more tests, and then it initializes the video. So any of these tests that are failing at the beginning can cause a halt without us actually knowing what the problem is. Now, looking at this Supersoft ROM, the difference is the very first thing it does is initialize the audio, and then it initializes the video. It does that before it does any other tests. If it can do those initializations without relying on DRAM at all, if you have bad RAM on the motherboard, then you should be okay and able to initialize those things. This diagnostic ROM is pretty useful in that as soon as it initializes the video, it gives you a bunch of status information. It shows you exactly which self-tests are running, and that's all these tests right here. So if something fails where normally the failure would be silent and you wouldn't know about it with the stock ROM, with this Supersoft ROM, you should at least hopefully have a video display that tells you what it is. And if the video can't initialize for some reason, you at least have audio, so we have beeping. I have a speaker right here, which I'll connect up to the motherboard. So before we actually switch the ROM, let's turn the computer on. So there's not even a beep coming out of the speaker. So that's just in case, if you notice here on the IBM post initialization sequence, there are some more tests that run after the speaker's initialized or the audio system. So if one of these were failing, we would hear a beep at least, but that's not the case. The article on -0degrees about this diagram is excellent. It has tons of useful information. If you're going to use it, I recommend you read through it carefully because there's a lot of good stuff, like the fact that this diagnostic ROM only works with CGA and monochrome. It may work with EGA, and it definitely doesn't work with VGA. So if that's all you have, you're not going to be able to use this ROM. It does talk about how some of the results that the diagnostic ROM can give you are very misleading, and that's no different than on a Commodore with the dead test, for instance, where you get flash codes. You might think you have bad RAM, but you actually have a bad PLA. So it's really important to remember that any diagnostic ROM on any computer you're using, the results need to be taken with a grain of salt because you just never know what other factors are going to be giving it false readings. Now, for the 5150 motherboard like this one, it says here that you have to put the diagnostic ROM into U33. And one of the biggest issues with using this ROM on this computer is that these ROMs are mask ROMs and they're 8K each. And the pinout of these is not compatible with the normal 2764 EEPROM. So if you only have the ability to create 2764 EEPROMs on your Mini Pro, for instance, you need to use an adapter in this board. And if we click this, there's a picture, I think, of it. There it is, it's a little PCB, and you need to get a PCB that's an adapter from a 2364 to a 2764. Those are pretty commonly available. Lots of open source ones you can download and have manufactured, or I think if you go on eBay, you can find and buy those. I'm going to be using a chip that I was able to program on my Data I/O EEPROM programmer. So it's kind of a rare and expensive programmer that very few people are going to have. So generally, if you're going to do this, you're going to need to use an adapter. But hopefully this chip should work in this motherboard without an adapter, because this actually has the same pinout as a 2364 ROM. And I've used these plenty of times in place of those. So hopefully that will work. So this EEPROM here that I'm removing is U33. That's the relevant chip. Let's put in my diagnostic ROM here. Okay. And I have the CPU clip back on, because let's just see, before I even plug a video card in, let's see if this does anything different. If it's just getting stuck immediately, then that's a bad sign and it may not even initialize the video card. I still have the speaker hooked up, so we might hear that beep. Let's turn this on. And it's just doing that, which is not a good sign. So it's not halting, but that does not look like normal operation, if you ask me. It's too repeating, this pattern here. I don't think this is actually working. There was no beep out of the speaker, but just for fun, let's put the video card in. And we're looking at the RGB to HDMI. Turn this on. Whoa, oh, hey, what? It's initialized. What? How come it doesn't beep? Okay, so it's actually running. So I guess it got stuck trying to initialize the video card. Critical memory region, look at that. One failure. So, wow, this diagnostic ROM was handy. So right now it's clicking on the relay right here on the motherboard. This is for the cassette output. Maybe there's something wrong. I would think we would have heard a beep. I actually don't know if this speaker is working. But I think on the 5150, the beep speaker is actually switched between the cassette output here and the speaker through this relay. So there could be a problem on that relay. But I'm really excited. So taking a look at this, it says 16K critical memory region, right? Which is that first bank of memory here that's soldered on the board. But over on the bottom right, it says failing bits 3. Actually tells us which bit it is, which is great because we can go look that up on the schematic and actually see which chip it is. On a good motherboard design, the layout of the motherboard would be like bit 0, 1, 2, 3, 4, 5, 6, 7, or maybe we start over here with 0 and through 7, but that's not necessarily the case. They can be randomized and mixed up. Let's look here at the schematic, see if we can figure out which is bit 3 is what we're looking for, right? Yes, bit 3. So up here you see MD 0 through 7. These are the data bits that are going through the address latches or the latches and the buffers and stuff like that. We're looking for bit 3. Now, there could still be a problem with some of the logic on this board because remember, MD0 is created, for instance, by this LS245. That's connecting the data bus 3 all the way through to the RAM. There could be a problem right there. And in addition, remember the data bus lines and the address lines on this computer are multiplexed together. So there's going to be a latch and some other logic that also controls that. The fact is it's mostly working though, which means that the control logic, the logic that controls this LS245, for instance, is working. This LS245 itself could be a problem, or potentially what's beyond on those data bus lines. But let's first start with the RAM chips. I'm not going to remove it from the board yet. Let's just look to see which one it is. So right here, it's U41. I'm going to write that down. What you need to keep in mind when we're thinking about data bit 3 is it's not necessarily the soldered chip that's bad. Even though it says it's the critical 16K region, which is this first bank of memory right here, it could easily be one of these other chips that's also on MD3 that's causing a problem. Now, if we scroll down, we can see that there are other things on this data bus. So there's MD3 right there, pin 11 on this 74S280. That could be a bad chip on that one line that's causing an issue. Also down here, these are the other RAM chips. So there's MD3. So this is on U57. Just going to write all of these down because these other chips are socketed. So it's much easier just to take them out of the motherboard. And it looks like if we scroll over here, this goes over to another page. So MD3 here is U73. And finally, this MD3 right here is connected to U99. And looking at the socket numbers that I wrote down on my note compared to what's on the motherboard, it is this chip here and these 3 chips in a row. I've gone ahead and I've removed those chips. So all that's left in the board is this one right here, U41. So let's turn it on here and see if that changes anything whatsoever. Okay, looks like it failed in exactly the same way. I know it's a little small, might not be easy to see, but I see that it's bit 3 that's also failed. So there we go. Okay, what's interesting is I hear it clicking the relay, and I noticed it clicked it 3 times, which probably is indicating that it's bit 3. So that's interesting that we're not hearing a beep though. I'm just going to test the speaker right here with the multimeter. Oh, yeah. 21 megohm. All right, that speaker's bad. That's so funny. I luckily keep a little assortment of speakers off the side of the bench here. So let's try this one here, which looks like it has normal PC wiring. Okay, let's see what happens now. If this beeps, I hear a click. That's a good sign. You know what's funny is I wonder if it was beeping. Look at that. Oh, okay. Okay, I think the manual would probably explain exactly what these beep codes mean. That was a lot more beeps. I thought it would have been like 1 high beep and then like 3 beeps for low. So let's see if it does another beep code. I wonder now if the stock ROM... Okay, well, I don't know. That did 3 beeps, right, for bit 3. Anyways, what I was trying to say is I wonder if the stock ROM was also complaining with a beep code. I'm going to switch back to it. So let's pop in this stock IBM ROM and let's see if it does beep codes. Because you know what? Maybe it was trying to tell me something. No, there was a click, but there was no beep. And we know it only took a split second for it to stop executing code based on what we saw on the oscilloscope. Alrighty, I'm going to unplug the speaker for a second because I don't want to keep hearing that beep code because that's pretty loud. I really don't think there's any problem with this RAM I took out of the board. I'm just going to leave it off to the side for a second. Let's probe what's happening on the data line on this RAM chip. These are NEC RAM chips, by the way. If I zoom in here, you can see it a little bit better. So I don't immediately think that there's any problem with those. We need to rule out that it's not any of the other things that are on the data bus, right? It could be that bus transceiver up at the top here, or it could be this chip right here. What was this, the LS or the S280? So looking at the RAM chips here, MD3, it's on pins 2 and 4. So we'll just clip on to 2 right here. Okay, is this okay? This doesn't look great. Notice it's like 3.7 volts and stuff like that. The best thing to do would be to look at one of the other chips, like neighbor chip here, and let's see how that looks. It looks pretty much the same on this chip that's adjacent to data line 4, so it's probably fine. TTL is quite tolerant to things not being 5 volts. Usually you can have stuff down to like 3 volts and it's gonna work pretty much perfectly. Now what's happening here is the diagnostic is frozen, but it's still sitting here doing stuff. And I think that's probably the RAM refresh or something like that. Let's just pick another random chip over here. All right, so this other chip here, yeah, the levels seem all about the same. So that's the important thing. I was just looking to see if the levels on that one MD3 line were weird and different than the rest. And they're really not. It's basically the same. And that kind of tells us right there that it's probably this RAM chip that has just failed. I just put the clip back onto the relevant chip, and yeah, I mean, it looks basically the same. Let's do the old feel test, see if this feels any warmer than the others. It doesn't. Feels exactly the same. So I'm pretty confident that this RAM chip here is the problem at this point. So I marked it there. I'm going to remove it from the board. We'll put it in a socket, and we'll see if swapping in a different chip gets this diagnostic running further. So I was watching someone else do a repair on an IBM 5160 the other day, and they were trying to remove the tantalum caps and were having the most difficult time doing it. Basically like burning the heck out of the pads on the underside of the board, just because the problem with the IBM 5150 and the 5160 is the motherboard has so much thick copper in it. It's just really well-made PCB that most soldering irons really struggle, and it wicks away all the heat. The trick is, if you're having trouble desoldering something from this board, just use hot air in addition to your desoldering iron. And as you can see here on the RAM chips, it makes super quick work of it, and it comes out perfectly without any fuss or trouble. You can also use a hot plate to warm up the entire board if you're going to be desoldering stuff, but for localized components like this, hot air is all you really need. All right, there's the chip, which we think is bad. It's pretty easy to take out. What I'm going to do is I'm going to insert one of the other chips into that spot, like so. In fact, we'll just stick these other ones in here as well. It's not that I know these other chips are good, but there's a good chance it is, and now we'll just get a RAM error on this bank right here. And before I power this on, I have a much bigger speaker to connect up. I think this came out of an old TV or something. I went ahead and I connected up the PC speaker wire, and I took the bracket that was on that other dead speaker and put it on here, although it doesn't really work because it's a bit too big. The speaker, that is, the bracket wouldn't be able to screw onto the case. Or maybe it would. I don't know. Anyways, we'll put that off to the side. All right, here we go. Let's turn this on. Got to click out of the speaker. So it is running the test. All right. Critical region. Uh-oh. All right, so I think it's telling us we have a problem here. Let's figure out which bit it is. Oh, it's still bit 3. Well. So I spoke too soon for this poor little RAM chip. I'm sorry about that. Let's put this back in the board then. I'm just adding a little voiceover here while editing. I'm glad I didn't dwell too much on thinking that this chip was actually good and there was some other problem on the board, because the bit 3 error that the diagnostic is reporting is on the 4th bank of RAM that I left the chip out of the motherboard. In hindsight, I should have realized it immediately, but I think I missed that point. But luckily, I very quickly moved on and figured out what was actually wrong with this board. All right, the original chip is back in the board along with all 3 of the other RAM chips. Let's turn this on. I'm going to unplug the speaker again because it's too loud for all the beeping. I want to see if it's talking about parity errors, because this motherboard here, if I get this into camera view, it has parity RAM right here. Now see, it says no false parity errors right there. And look there, it says parity error at address C000. Now we have to remember that this first bank here is 64K, and that right there is in that first bank. And there it says parity error at 8,000 as well. I'm not really used to working on systems that have parity memory, so I think it's possible that the parity memory chip is bad as well, or the part of the circuit that has to do with that parity memory chip. Let's pop in a known good RAM chip, and I'll leave the other ones in place since it seems to be testing all of those banks. And I want to see if that parity error changes at all. I'm slightly suspicious about what's going on. Okay, so that's a known good chip and it's in there. Let's power up the system again. Let's see what it does. All right, so parity error at address 5040. So that's different than what it said when this other RAM chip was in here, the one I just put in there. So maybe this parity chip that's over here is also problematic. What I can try doing, piggybacking this other good RAM chip on top of it, and we'll see if that does anything. I'm just gonna hold the RAM chip on here, see if that does anything. Now, of course, when a RAM chip is bad and you put another one on top of it, it doesn't always work, the piggyback. Now, there's still a parity error at the same address. Alrighty, let's think about this for a second. The parity RAM chip can definitely be bad, because when parity RAM chips fail, that causes parity RAM errors that aren't real. Now, if you're not familiar with parity RAM chips, and I haven't done a lot of work with them, it's essentially a 9th RAM chip. When you have 8 for 8 bits and you have a 9th chip, that's like a error correction chip in a way, or error detection chip. Actually, it doesn't correct errors, that's ECC. It just detects errors. It allows for kind of like a checksum to happen. And if it goes to access a memory location and that bit doesn't match a pre-existing calculation that was then stored in that chip, then that triggers a parity error, which will crash the system. Now, if the system were running and you get a parity error, it will actually print parity error. That's a non-maskable interrupt. But because this particular error seems to exist within that first 16K of memory, well, that prevents the original ROM from actually initializing the video card at all. I am curious though, now that we've changed it and that parity error address is a little higher, it was at 5040, let's put the original ROM back in and let's see if this can initialize the system. You have to remember that the IBM PC can work with just 16K of working memory. If everything else after that is bad, that's enough for it to initialize. And that's because the very original version of this system actually had 16K of RAM as the minimum RAM configuration. So that's why it can work with just 16K. I'm not sure if later BIOSes could, but at least the 5151 should be able to. So the original ROM is back in the board here. Let's turn this on, let's hook up the speaker. Aha, look at that. So, okay, so the original ROM is causing it to beep. Well, here I am with a voiceover again because I just noticed while editing that it actually initialized the video card and said parity error with a memory error on there. So I'm about to go into a little bit of troubleshooting on that beep code that obviously I could have shortcut if I just saw that it initialized the video. So please bear with me on that. That definitely tells me that this RAM chip right here is bad, but I also think the parity RAM chip is bad. Now what's happening is this RAM was bad in that first 16K of memory, and that prevents the actual BIOS from doing anything. It doesn't even initialize the speaker. But with a parity RAM error higher up, I think what's happening is it doesn't initialize the video card, but it at least initializes the speaker. Remember when we saw that particular picture on -0° and it shows the various steps and initialized audio was first. So whatever's happening now is causing it to get to the point where at least the speaker is initialized and then it fails. So again, I think it's because the parity memory error we're getting is higher up in the RAM above that 16K boundary, which does allow the system to at least kind of post. Let's just turn it on. Let's listen one more time and see if we get that beep. There we go. Okay, wait, it beeped, long beep, and then 2 beeps. I think there's a beep code we can go look up in the IBM technical manual to see what it's telling us about this particular error. I'm on -0°, and of course they have the post codes here. So 1 long beep, then 1 short beep. Okay, that's not what we're getting. Okay, 1 long beep, 2 short beeps, cause. Configured switch 1 as MDA, configured switch 1 as CGA. A video card with BIOS expansion ROM did not test and found a problem. Or a bug in the post. See description of C800 ROM below. Well, we know that the video card is working. Is this actually in the board? Yeah, it's in the board. We saw the video card working. I've used this video card before on the test system in part 1, but it initialized it fine. Also, it seems like we're getting lied to here. See description of C800 ROM below. Expansion card with the BIOS expansion ROM, and the ROM is partly at fault or corrupt contents. It's used in hard drive controllers. Oh, well, we don't have any controllers in this thing. Well, clearly, the beep code, not particularly useful. It's telling us there's a problem, but that's it. I'm just curious, is there even a beep code for parity error? No, it doesn't really seem like it. All right, so I'm going to pop this out. You know, this had me thinking too. It's quite possible that these other ROMs are not good as well. Like I said, I've had problems before where these ROMs go bad, and I don't think the diagnostic ROM that we're running here gets to testing the ROMs yet. I'm not even sure it does test the ROMs, but it's definitely getting stuck on the RAM, which means that, well, there could be a ROM problem, and maybe that causes that long, short beep. Let's turn this on one more time. And there it is running, and yeah, we're getting exactly the same thing. So parity error at 5040, and it's gonna fail. So the next logical thing to do is let's find where the parity memory is on the schematic here. I don't wanna just go removing that parity chip here without trying to figure out how the parity memory works. It's this one right here. So this is driven by, oh, it is driven by this chip right here, the 74LS280. I see the output of this gate right here is also going to this parity RAM chip. And what about down on the next page? There must be, I guess, see this line right here that comes off the top, goes over here into this branch down here, and this branch right there ends up here, and there it is, MDP, so parity bit. So this gives us a bit of an idea where to look next. So we have the S280 chip that we need to look at, the LS125, that gate right there. Looks like it has an output that goes to those RAM chips, but it also, what does it do? If it has a write enable pin that goes in there, that's probably fine because lots of other stuff would be broken if that were bad. Looks like there's an output here that makes its way over here to this gate, MDP, so that's coming from there. Looks like there's another input right here to the S280 that comes from this gate right here, U97. Looks like it has a feedback from itself, but it goes through that gate, U83, and this XMEM MR line. Again, if that line were bad, I don't think anything would be working because it controls the direction on the LS245. This is the bus transceiver that connects the RAM to the rest of the system. So I don't think that line is bad, but this gate could be problematic. That gate could be problematic. And let's see here. Yeah, and then obviously this chip could be problematic, or this chip. I am thinking though that if any of these gates were totally broken or not working. And I don't think the parity memory would work at all. And it would probably cause parity errors on more than just bit 3, which is all we're seeing. Okay, so back on the diagnostic screen, let's just take a look. It's been running for several minutes here, so it looks like it's done multiple passes. This thing has actually run through a lot further. So it's actually showing system bias ROM 1 failed at U28. That could be a problem, but that might be a false positive. I know there's a bunch of false positives with this particular ROM, so we need to take everything with a grain of salt. I am going to write that down, though, that maybe U28 is problematic. Now, looking down at the bottom right, we have parity error at 8E81. So that's in that first bank of memory. That's this first bank right here. Doesn't even show any failing bits anymore, which is interesting. So we may be only dealing with parity errors. But the thing is, the parity error there is in that first bank, and it's not in these other banks. And it looks like it's tested all the memory, because it says system memory tested at the bottom left there to 40000. The top of memory on this motherboard is 3FFFF. So it's basically tested all the memory, and it's only telling us we have a parity error there at 8E81. Now, it also says slow refresh. Now, I recall seeing in the -0° article about this ROM that can show up, and that is something you can ignore, or it's false positive. We'll have to go back and take a look at what that says. I think we need to focus on the parity error problem first. So I am really leaning to this parity chip right here being the bad one based on the diagnostic information, but we do need to double check that this stuff right here is working, that the output on here on pin 6 of UE80 looks right, and the output of pin 5 here on this 280 also looks correct. Let's start with that 74S280. Note that it may not look like pin 5 where I'm connected, but that's because this is offset 1 row of pins. This clip is actually a little bit too big for that chip, and there's a resistor right here which is in the way, so I have it offset 1 pin. So we're on pin 5. Let's look here, turn this on. Alrighty, so we are running right here. I mean, that signal looks totally fine. Obviously, if there's a problem with that chip that's internal to it, like it's not one of the output drivers or something like that, like the other failed chip that I already replaced, it can be harder to see. The only way to know for sure if this chip were behaving correctly would be to hook up the logic analyzer to it and look at all the inputs and look at the output as well, and then compare that to a truth table. But I'm going to say that this output 5 here looks okay. We're not seeing anything that looks unusual here. So let's check out this gate right here. Next, let's look at U80, which I have the clip on right here. We're going to look at pin 6, which is the output that goes to the RAM chips themselves. Let's turn this on. Wait, what? Let's double check that I'm on the correct pin here. Yes, U80 right there on the PCB, and it's an LS125, so it's the correct part. And again, because I have the wrong size clip, let's just make sure I'm on pin 6. 1, 2, 3, 4, 5, 6. Alrighty, we're hooked on. Let's turn this on. Zooming out here, we see occasional bursts of normalcy, like that right there. I don't think that's correct. Let's take a look at the datasheet first, just before I jump to any conclusions. I don't know off the top of my head what an LS125 is. Well, it is a tri-state buffer. That means that depending on the input signal going into it, it won't enable that line on the output, which means it could just float, actually. I have the oscilloscope probe on pin 4, which is this input right here, the right enable pin. Let's see how that looks. Okay, totally normal. In fact, well, okay, actually, now we think about this. So when that line is low is the only time that this particular chip is going to be outputting anything. And it's currently not outputting anything. Well, there it is. Now it's outputting stuff. So there's all sorts of activity happening on that pin 4. And let's look at pin 5. Lots and lots of activity happening on pin 5. That's the output of the S280 there. And if we go to pin 6, I'm going to power cycle the computer, because we saw when we turned it on, there was all sorts of activity on that right enable pin. That doesn't seem like it's working correctly, or really, it doesn't. All right, so let's think about this for a second here. We have to remember, let me zoom out a little bit. We have to remember that this chip is generating a signal that is going to all of the 4 parity RAM chips, and that output goes to all of them. So it's possible that one of these chips is bad as well, and it's holding that level at a strange place. So the first thing I think I want to do is find my little chip lifter. Here it is. We're going to take out all of the parity RAM chips, these other ones as well. So I'm clipped onto pin 6, which is the output of the gate in question, and let's turn this on. Nah, that still looks weird. The problem is here, again, is I don't know if the problem is this RAM chip that's causing all the issues or it's this chip and it has a bad driver on it. I think the only thing I can do at this point is I'm just gonna snip the leg by cutting pin 6 right here or pin 2 and 14 on the RAM chip, the one RAM chip that's left in here. We're gonna disconnect those two chips from each other. Now when you snip something with these side cutters, I know it seems draconian, but unfortunately, sometimes you're just left with a situation like this where two chips could be bad and you're not really sure which is which. If you just cut the leg, you can always resolder it relatively easily without like any evidence that you've done it. There'll be a little blob of solder there. The question is, which chip is more likely to be bad? The RAM chip, which I have my finger on, or the Fairchild LS125? I'm honestly not sure. The fact is we already had a bad RAM chip, which implies that another one could be failed, but we already had a bad logic chip as well, and it wasn't the same brand as this Fairchild. That was something else that went bad as well. So you kind of have to guess, and it's 50-50 at this point. If I cut the leg on the Fairchild chip right here, then there's only one leg I have to resolder that if that makes no change. And if it doesn't make a change, then I'm going to have to remove this chip anyways. I think it's the bad RAM chip. But I think even though we've had a bad RAM chip, I'm going to go for the bad LS125, and I'm going to snip that leg. So we're looking for pin 6. 1, 2, 3, 4, 5, 6. I'm just going to cut it about halfway up. That should be disconnected now. It may not be super easy to see, but it has a cut in it right now. So that is floating. So if I check the output on the top side here, which is on the package, I'll be able to see what that signal looks like without the RAM chip interfering with it. Alrighty, here we go. Let's see what it looks like. Oh, I don't know. I don't think that looks correct still. Now it is a tri-state buffer, remember, so it only goes up and down when it's being signaled to come on. But I think it's signaled to come on quite a bit more often than that. There's a whole bunch going on right there. And all of that should be writing. We should see that pin active as it's writing information. I think this chip is bad. I think it is. You know what though? Look at this. When I zoom out, it is low. It's at ground here. And then I don't know. I'm not sure if this is working correctly or not. So the diagnostic is running and we should see nothing but parity errors at this point because the parity is disconnected entirely, right? So let's see if anything changes here. It's obviously, oh, there it is. Parity error 4,000, C,000, 14,000. So tons and tons of parity errors now, which makes sense because there's nothing being written to those parity RAM chips right now because I cut that leg. This kind of tells me right here that the parity is working and that LS125 is working normally. When I was running this before, we didn't see parity errors in those upper RAM banks. We only saw it down at that low address. So I think I am moving back towards believing that this chip is the problem. These are fine, and this chip here is fine as well. So I'm gonna reconnect that leg, and then I'm gonna remove this chip from the board. We'll socket it, and we'll see if that fixes this problem. Alrighty, the chip has been socketed and I stuck in a new chip and I have a check mark on there because I think it's one I've tested before and it works. And I reconnected that leg that I cut on this chip and I double checked that from the top of the package there over to the RAM chips, the parity RAM chips. I do have continuity to pin 2 over here, so I know it's reconnected. All right, the video card's back in, the power is connected to the motherboard. Let's turn this on and see what happens. Okay, are we going to get parity errors? Did I change the wrong chip? I didn't ruin the chip. It's right here. Let's see here. Oh, hey, whoa, 16K passed. So now it's testing memory refresh, and this is where it might say that slow refresh thing, but alrighty, so this chip right here, definitely a problem. We will test all of the bad chips so far that we have found in the Retro Chip Tester Pro. Hey, look at this. This is testing the CGA card. Numerical processor not present, keyboard controller. There's no keyboard controller, by the way, on the 5150. So this is going to give an error. That I know so much. But we didn't get that slow refresh thing. So that refresh error was definitely caused by the parity error. So I'm glad we didn't go troubleshoot that first and we stuck to the parity error problem. And this diagnostic ROM is just sitting here on floppy read. I assume it's going to fail and then move on. I'd like it to do the rest of the testing. Oh, here we go. It's making the clicks on the relay. While we wait for this to run, I am kicking myself that I cut the leg of this Fairchild chip here. I'm doing a quick voiceover here just because I wanted to clarify exactly what I did wrong, and I feel that the way I described it on camera wasn't actually descriptive enough. One of the problems with this diagnostic ROM, and is also partially due to my unfamiliarity with it, is that when it shows a memory error, it just briefly shows it, and if another subsequent error happens, it overwrites the previous error. So you don't get a list of errors, you just have to quickly look at it. What I should have paid attention to is once I replaced the bad RAM chip on bit 3, the only thing being reported was a parity error at, I think, 050E or something like that. It was a parity error in that first 64K of RAM only. The diagnostic ROM went and tested the rest of the memory on the motherboard, and all of that passed without any further errors. That includes all of the parity memory tests for that upper 192K. Because the output of the LS125, the parity memory signal, goes to all 4 of the parity memory chips, the fact that that upper 192K was completely passing all RAM tests, including parity tests, should have told me that there was nothing wrong with the LS125. And because of that, that tells us right there that the problem was the parity RAM chip on that first bank of memory. So I apologize, Fairchild LS125, for cutting your leg erroneously, for accusing you of being bad when you were not bad. The badness was entirely the NEC RAM chip there in that parity socket. All right, there we go. Slow refresh. That totally passed. So now it's doing the BIOS ROM tests, and let's see about this U28 thing. Okay, so that's still failing. I haven't gone and read up on -0 degrees if that failing is actually a problem, or is that something related to the version of the ROMs that are on here, or some other reason. The easiest way to tell, I think, is to swap out the ROM, the diagnostic ROM, and to put in my original system ROM. And let's see if this thing can work. We're so close. We are so freaking close. I can feel it. There it is. Let's plug the speaker in so we can hear those IBM beeps. Here we go. We are, oh, cursor. Okay. It freaking works. It's freaking working. So that was it. That long, short beep code was a parity error beep code, a parity error in the 16K of RAM. And I don't know if the -0 degrees is missing that information. There we go, booted right into basic. This computer is freaking fixed. That is so awesome. Wow, okay, well, like I said, I don't know if -0 degrees has incorrect information or incomplete information on what long, short beep is, but we can see now that that beep code was definitely telling us that there was a bad parity RAM chip in that socket there. Let's do a little bit more testing with the XT IDE. I think I should plug in a floppy drive controller as well so we can test out the DMA on this machine, because the floppy drive controller uses DMA. All right, let's see what happens here. So XT IDE may not boot because I think I have DOS 622 on there, and obviously that may be a bit much for 256K of RAM. I have RAM expansion cards. I don't know where they are. They're not handy. So we're going to try this DOS 3.3 disk here if it can't boot off the XT IDE. Incidentally, it's normal that it doesn't show like how much memory you have right here. The 5150 BIOS does not count up the RAM as it checks it. It just does it silently. Oh, 301, you know what? I have the keyboard set to AT, not XT. This is a switchable keyboard, so we'll just switch this over. It is booting the disk though, or it was attempting to boot the disk. Actually, look at that, 4054-201. I think that's a RAM error. I'm gonna power cycle the computer one more time here. Okay, so no 301 error, and that's because the keyboard is set to XT mode, but 4054-201. I think that's RAM. I think there's more bad RAM. It's trying to boot the disk here, and it goes for a little bit, and I think it's just gonna stop. Yeah, it's not booting anymore. Let's investigate 4054-201. 201 is displayed on screen. This is a RAM-related error. For the 5150, 201 will be prefixed by a 2-byte, e.g. 0410, and it is normal to say parity error if possible. For the 5150, 201 will be prefixed by 2 bytes, so that's 0410 is their example. There are a bunch of causes. You could have incorrect switch settings. I'm feeling like the switch settings might be the problem because the RAM test was working fine in the diagnostic ROM. So we might need to run that again. More information on the RAM is here. And here is a decoding table. First 2 digits tells you which bank it is, and if it's anything up to 9F, then that's going to be in the extra RAM, which this machine doesn't have. And take a look at that, 4054. 40 implies that it thinks there's an expansion RAM on this machine, which there isn't, so of course that's going to fail. And it is switch 2 that tells the BIOS how much memory your computer has. So if it thinks you only have 256K, it's only going to test that much. But if it thinks you have more than 256, it's actually going to try to test above the boundary where there is no physical RAM on this computer. I don't have an expansion card in here, so it needs to stop at 256. And actually it says that right here. If you set switch 2 to higher amount than is fitted, you will get a 201 error code. So let's check the settings here. 256K needs to be switch 1 on, off, on. Well, and it looks like maybe in my jostling of the board or handling the board or flipping it over to desolder stuff, I did flip this switch. This switch here should be like that. It was set wrong. So I'm going to power cycle this and we'll turn it on again. The reason why DOS wasn't booting, I think, was because DOS also looks at the BIOS amount of memory and it tries to use all the memory it can get. It needs to not use anything above 256K because that memory doesn't exist. Okay, so let's try again. Cursor's flashing, disk drive's plugged in, keyboard's ready. Oh, look at that, no errors, no errors. Let's see if this thing can actually boot. Seems to be booting. Come on, come on. Is it gonna work? Oh, it freaking works. Look at that. This computer is fixed. The disk drive is working. Oh boy, oh boy. That feels really good. That feels really good. Incidentally, this is a mod player, but I don't think it's gonna work. There's no sound card on this machine. Let's just try loading it anyways. And we'll try picking up a small mod file here. I mean, it's not gonna work. There's no sound card, but we'll just see if it can load. I don't think 256K is enough. Galaxy Mod Player, there it is. It is compatible with the XT. It can run, but there's just no way. There's not enough memory on this thing. It's gonna crash out. What's good here is that the floppy drive is testing the DMA capability of the motherboard. I think it's crashed. I think it was trying to load into 640K. And there is no 640K. There, hit Control Delete there. The floppy drive interface is a good test of the motherboard because it uses the DMA circuitry. And I had a motherboard I was fixing once with another XT, and there was something wrong with the DMA on that board. And when you tried to use the floppy drive, it would always hang and freeze. And that was specifically because there was some logic chip that was bad. And anytime the DMA was called, I think it would go to the wrong DMA channel or something like that. And then it would cause the computer to crash. But we were able to boot DOS 3.3 here, so this is good to go. I popped the XT IDE back in. I want to see if it's able to recognize the compact flash card. That would be fun. I don't think it'll, oh no, there it is. Oh, InnoDisk, okay. Let me hold down Shift. DOS 622, does it work for 256K? It does work with 256K. Memory, there must be very little free. There it is, we can load a 200K program. Does Checkit work? Let's see. I don't think Checkit's gonna work. No, program is too big to fit into memory. Maybe MIPS will work. Yeah, okay, this is a little bit of a benchmark here. Let's just make sure this computer is running at bone stock speed. Yep, there it is. IBM PC, 4.7 megahertz, 1.0. Right on the nose. Every single benchmark there was an exact 1.0 because, of course, this was timed against an IBM PC, and this is an IBM PC. We could try running Norton Commander 2. Let's see if this works. Oh, that works. That can run into 56K. Let's try running Jim Leonard's CGA compatibility suite. Does this work at 256K? Oh, I think it does. All right. So we can see here that this VTech CGA card that I'm using here is fully CGA compatible. We'll be able to get some of the cool effects here. Look at those raster bars and all that. Bringing it a nice 60 frames per second as well. Ooh. And this is one of the relatively new versions of this program. And take a look at this fancy graphics mode it can do. Not this one, this one. That is coming out of a bone stock CGA card. A CGA card from 1981 with the IBM PC5150 would be able to display this perfectly on the original monitor. It's using some trickery with the 6845 CRT controller to basically, it's a text mode that has the letters shrunken down. We're only seeing a little bit of each letter, and that can enable you to have more colors in what looks like a graphics mode right here. I have a game called Pacu here. CGA card. Oh yeah, this one too. This is like Pac-Man, and it's using the same mode. And look how good this looks. Let's see if there's music as well. Plug the speaker back in here. Okay, so far no music. Sound is on though. Enter to play. Okay, it's all right. It's Pac-Man-like. Okay, I'm gonna unplug the speaker because it's loud. I mean, this looks really good for CGA, which everyone thinks is so terrible. Look at the colors. The colors look great. Uh-oh, getting chased. Ah! Whoa! All right, I'm not playing very well there. All right, it's enough fiddling around. I think I've pretty much confirmed that this computer is working perfectly. So what I want to do now is I have the Retro Chip Tester Pro here. Let's test out those bad chips that I took out of this machine. We had 2 bad RAM chips, and from part 1, we had that logic chip. So let's see if those chips all test bad on the Retro Chip Tester Pro. I was trying to avoid using the tester the entire time here because it's not something that a lot of people have. And I wanted to show that you can fix stuff like this without having such devices in your arsenal. Okay, so first chip to test is this one here, which is the 74LS00. So we're going to go in here. We'll just start right there. And right away, it failed. Let's just do it again. Yep. Okay, so we knew that chip was bad already because the levels were obviously completely wrong. And you don't really need a fancy tester like this to know that because I just had to look at it to see that it wasn't working properly. Okay, here's one of the bad RAM chips here. Let's see if this tests bad. Okay, that failed right away, so that's definitely bad. Let's try the other one here. Let's see if this one. Insert, wait, what? It doesn't even think I have one in the tester. It doesn't even see it as inserted. All these chips are bad, but we already knew that, but people like to see that on the tester, so there it is. And the last thing is, let's put these in the dead parts bin. This is not something I always do, and people are always like, where's the dead parts bin? Well, I haven't shown in a while what's in here. Of course, every time I have a dead part or a bad part when I'm doing a repair, even if I don't show it, the dead parts do go into this bin here. So as you can see, there's a bunch of RIFAs in here. There's a Cyrix CPU, there's RAM. Like what's this? That's some MOS chip from a 64. So there's lots of stuff. Yeah, all the repairs, they go into here. So these 3 chips here, goodbye. They're bad. So there we have it. That is one fully functional 5150 motherboard, fully repaired and diagnosed with only one mistake made, and that was me cutting that leg on that chip, which I had to resolder, and it's okay. It didn't damage it or anything, but I'm definitely going to put that in the column of a mistake I made because the logic was there, and I should have been able to tell from what we were seeing that it was the RAM chip, the parity RAM chip, specifically because it wasn't telling me I was getting parity errors in these other areas here. It was only happening in this first 64K bank right here. My intent for these repair videos is to try to teach the methodology that I use for doing repairs on electronics. I have only been doing this a few years, but I've learned from some really smart people who are way smarter than me, at good techniques for trying to figure out and isolate problems on boards. With motherboards like this, there are definite things on here that seem to fail more than everything else. I'd say the RAM is one of them and the ROMs is another thing. The thing is, if we had changed out all the RAM and swapped out the ROMs, it would have been a pain to do both because of all the desoldering required for the RAM. And then the ROMs, you have to make adapters or use these special EEPROMs, which pretty much no one can program. The motherboard still wouldn't have worked because it was this logic chip up here that was actually preventing the whole computer from working at all. So it's really about using logical deduction and logical reasoning to try to think through the problems that are happening on a computer and looking at the signals you're seeing, either with an oscilloscope or a logic probe, and try to get to the bottom of what the problem is. And in part one, I slowly worked my way back to figure out it was this logic chip. The computer was then working better, but then it was still getting hung up. Well, it turned out that that post process that IBM built into the ROM here is pretty lame because it craps out at the first sign of problems. So this diagnostic ROM then really came to the rescue to help us identify those additional problems, which were 2 more soldered RAM chips. Anyhow, I think I'm going to end this video here. I think I've sort of babbled on for long enough. If you enjoyed this repair video, I would appreciate a thumbs up. If you didn't, you know what to do. Thanks to my patrons. Their names are going to be scrolling up the side of the screen. They get early access to videos and things like that. If you have any comments, I'd love to hear them down in the comment section below, and subscribe if you haven't already. And I guess that's going to be that. So stay healthy, stay safe, and I will see you next time. Bye.